Hi, my name is Nick Warner, and this presentation is on CrowdGPSSec, leveraging crowdsourcing to detect and localize GPS spoofing attacks. I'd like to start out with some of my background. I have a degree in computer science and a minor in cybersecurity. Additionally, the most relevant to this paper, I'm a professional pilot with a practical knowledge of air transport, navigation systems, radar, and signals. As such, I find this paper very interesting and the topic in general relevant. I look forward to any questions or discussions. First, some acknowledgements on the screen. We have our 6 authors there. Jansen, Matthias, Schafer, Daniel Moser, Vincent Lenders, Christina Popper, and Jen Schmitt. We have a spattering from Kaiserslautern, from Bochum, Germany, from Switzerland, and also from Abu Dhabi. This was presented in the 2018 IEEE Symposium on Security and Privacy. Introduction. Bottom line up front, CrowdGPSSec is easily implemented and leverages existing ATC and aircraft infrastructure to identify and locate spoofing attacks in less than 2 minutes to around 150 meters accuracy and 15 minutes of monitoring. The basis for this, GPS has become the first choice in navigating and tracking outdoors. More than 1 billion devices rely on GPS. We all use it in our daily lives, either on our person or in our cars, or in the infrastructure we rely on to live daily. Aircraft are vulnerable to GPS spoofing attacks, and indeed civilian GPS is by its very nature vulnerable, to include GLONASS, Galileo, Beidou, and others. The equipment cost to perform these attacks has dropped dramatically. We're talking sub-$1,000 range. While countermeasures exist, and may be preferable in industry or military applications, CrowdGPSSec detects and localizes attacks without requiring updates to any existing infrastructure. So, to be clear, this is aimed at the civilian and commercial industry. Military and government applications have additional safeguards and capability, as well as things they need to worry about. The abstract and motivation. Aviation's reliance on GPS for navigation and air traffic monitoring creates new risks for air safety. The aviation industry's increasing reliance on GPS to facilitate navigation and air traffic monitoring opens new attack vectors with the purpose of hijacking UAVs or interfering with air safety, aircraft themselves. CrowdGPSSec is proposed to detect and find GPS spoofing attacks on airborne targets. It doesn't require any updates to the infrastructure like we talked about on the ground or with airborne receivers. Utilizes crowdsourcing to monitor GPS advertisements. We're talking about ADS-B or FLARM if you're in Europe. Existing countermeasures and their problems. Cryptographic techniques are not resistant to replay attacks. Those aim at authenticating signals from satellites with additional signals that are unpredictable to users that do not own a secret key, what you would normally think of as cryptography. I'll add that this is only true in non-randomized cryptographic signals, so a concern in civilian applications, whereas military and government applications are a little bit more robust when it comes to that. But any of this does require changes to the infrastructure itself. Detection at signal level impose modifications to existing receivers, so based on anomaly checks in the physical signal waveform, and direction of arrival sensing. These impose modifications to existing receivers as well, and these are based on measuring the angle of arrival from which the signal is originating. The proposal for CrowdGPSSec aims to detect and localize attacks without modifying existing infrastructure. It can globally detect GPS spoofing in less than 2 seconds, localize up to an accuracy of 150 meters after 15 minutes of monitoring, and relies on indirect measurements of the spoofer by analyzing the position reports broadcasted by an aircraft. So it enables us to detect and localize a spoofer even when there is no direct line-of-sight connection from a sensor to the spoofer. Maintaining a line-of-sight connection to the aircraft is much simpler and thus more effective since the aircraft are in the sky and use high transmission power levels, which render the signals receivable from the ground up to several hundred kilometers away. Another major advantage is that CrowdGPSSec relies on data from air traffic monitoring sensors that are already widely deployed around the world, and it does not require a dedicated GPS signal acquisition infrastructure for spoofing detection and localization. So understanding GPS in aviation. GPS, as we know, satellites in orbit with atomic clocks and precise orbital parameters, so measurement of time to determine distance and comparison of distances to determine location. So 30 satellites located in the medium Earth orbit, more than 20,000 kilometers above the Earth's surface, GPS-capable receivers can determine their position in time by measuring the time of arrival from at least 4 satellites, and this is known as time distance of arrival, at least in aviation. ADS-B begins coming online in early 2000s, and that's to facilitate transponder and radar systems to help them better locate aircraft and provide for a tighter air control picture. And then a proprietary technology is FLARM, which the researchers used, which is similar to ADS-B, and it begins coming online in the early 2000s. This paper notes smaller vehicles tend to use FLARM, while larger tend to use ADS-B. And while this might be true in Europe and other parts of the world, in the US at least, this is not played out. ADS-B is ubiquitous and mandated by the Next Gen ATC initiative. In Europe, FLARM is more widely used, but it's proprietary and uses proprietary code and encryption. The paper notes that radar and INSs were the two main localization technologies used in aviation until the advent of GPS, which is preferred because of its superior accuracy. While this is partially true, I'd argue GPS is still a supplement to a more overarching blended system. In reality, at least in modern commercial and military applications, most aircraft fly on a blended solution of GPS and inertial navigation units, usually with redundant INUs and with monitoring systems in place to detect INU drift, GPS drift, bad signals, etc. Understanding GPS spoofing. A spoofer essentially transmits a false time or position at a stronger signal than the weak GPS signal, causing the receiver to lock onto the malicious signal. Exploits lack of authentication encryption of civilian GPS, can be imitation signals or saved signals rebroadcasted, what is known as a replay attack. It can be omnidirectional, though this is more common with jamming, but it still could be. It could be directional as well, and that's more difficult to detect and localize just by its nature. Assumptions and spoofing experiment setup. So CrowdGPSSec relies on 2 assumptions. If a receiver locks onto a spoof signal, it will broadcast that false info. So this would be an ADS-B or FLARM message. The spoof signal will affect more than just the targeted aircraft. And that's fairly true. It's very difficult to target a single aircraft, especially with beam widths at that distance. The experiment setup, you can read there, 2 transponders, a power FLARM core and a power FLARM portable, a USRP B200, a GPS spoofer, software defined for that as well, and a Raspberry Pi to run it all, RTL SDR software defined radio dongle, Flare open source FLARM decoder, and omnidirectional antennas for all devices. Spoofing experiment results and coverage estimation. Confirms an attacker can control position and speed of the FLARM devices. Deviation becomes larger with speed, as shown in figure 3 here. Commercial transponders do not perform plausibility checks on GPS input. Again, I would say this is only partially true from my experience. My aircraft certainly does, and most commercial GPS have a figure of merit that will indicate less than ideal conditions to include jamming and spoofing, so we can monitor that real time. Finds an attacker that can achieve a signal power of 15 decimal meters with an antenna capable of 12 decibel main lobe, and can affect aircraft within 34 kilometers at the average GPS signal. An attacker will, of course, look to exceed these base levels to ensure target lock-on. So inclination and beam width are important, as shown in figure 4. Researchers believe it is impossible to achieve both an inclination and beam width to perfectly target an aircraft. Therefore, secondary targets will be affected, and CrowdGPSSec will be effective in dense airspaces such as Europe. A base beam width of 0 degrees would indeed be able to target a victim. This, however, is impossible to achieve in practice and would also be very sensitive to small orientation errors. If you can just think about trying to hit an aircraft 100 miles away with a 0 degree beam width. CrowdGPSSec itself, it utilizes the Open Sky network, and this network is just a mostly voluntary, large ground-based sensor collection, just a mesh network of people monitoring air traffic. It has 3 modules that run on every position report. So multilateration is one module. It estimates aircraft location based on time difference of arrival, and that's where the multiple ground stations comes into effect. Spoofing detection cross-checks broadcasted positions with MLAT-derived positions, as well as between broadcasted positions between separate aircraft. And then spoofer localization triggered when the decision module has detected a spoofer. Something about MLAT there, this module is fundamental to CrowdGPSSec as it allows us to determine the true position of the aircraft independently of the content of the advertised messages. So even if an aircraft is putting out bad messages, we can still determine its location. MLAT. Areas of high sensor density allow for multiple sensors geographically separated to receive position advertisements. A position report contains the position of the aircraft, which is GPS derived, and a timestamp. Multilateration can be performed with 4 independent receptions of the same report. And geometrically, this is important because each relation describes a hyperbola in 2 dimensions and a hyperboloid in 3 dimensions. The intersecting points of all relations indicates the aircraft position as shown in figure 7. And so 4 would be about our minimum to get any sort of reasonable accuracy. Obviously, the more the better, but it is diminishing returns after that point. It's not usable to find the location of the spoofer, however, just the aircraft, and to find differences. More would be needed. Spoofing detection. Time alignment of transmissions is what we're talking about here. Position reports are broadcast at varying times for the same aircraft. For this module, those reports must be time aligned to a reference global time. This is done with the results from the MLAT module. So first, the time is found at which the report was issued. This is the transmission time by correcting for the Euclidean distance and the transmission speed. This equation here, the researchers used this to find that Euclidean distance, and then second, interpolation is performed to approximate the aircraft position at a global reference time, and so this is the reference equation. After this, all reported positions can be compared to the same time basis, and so the remainder of this presentation and paper assumes a time-aligned position. Test 1 is spoofing detection, cross-checks with MLAT. Cross-checks of advertised positions with MLAT derived estimated real positions. Remember, that's independent of the broadcast messages. The checks on each aircraft by the modules can be run independently and also in parallel. So where the first variable A at I is the real position of aircraft I, and the second is the reported position of aircraft, the second position of reported aircraft I, distance is the Euclidean distance function, and T1 denotes a predefined threshold which tolerates the measurement errors in the actual reported positions. Therefore scales linearly with the number of aircraft, so O of n. Our second test, spoofing detection, is multiple aircraft comparison. Perform comparison of advertised positions of multiple aircraft. When more than one aircraft receives the same spoofing signal, they will appear at the same location because it's the same broadcast. The time differences of individual GPS satellites are matched on the spoofer's radio transmission. With the knowledge of IFR separation minima, it is fairly easy to filter out aircraft that break the border in their separation. And in fact, this already exists in modern ATC software to generate alerts for controllers. So this equation considers pairs of aircraft, so it would run at O of n squared. However, this can be reduced by implementing nearest neighbor search trees. The researchers find this reduces complexity to O n times log of n. We have the same Euclidean distance equation from before, but I and J denote 2 different aircraft, and T2 is a threshold tolerating the GPS positioning of noise. Spoofing detection complementary design. So, because of this, the researchers propose running both tests in parallel. They believe in combining the tests and running one test on the other's results can overcome the pitfalls of the other, leading to a more robust detection confidence. GPS spoofer localization. Once detected, the goal is to find the spoofing device. While aircraft that receive the same spoof signal will report positions on the same track, they will report at different times due to the propagation delay of reception from the spoofing source. Aircraft that receive the fake signals earlier, so closer to the device, will be ahead on the spoof track. Aircraft that receive it later will be further away and behind on that track. Derived positions can be multilaterated to produce a location. So 4 derivations preferred for our paraboloids there. And 4 locations can be 4 aircraft, or same aircraft at 4 different sample times, or any combination thereof. We have the Euclidean distance algorithm once again, but here we have A and I and A and J of the MLAT derived actual aircraft positions of 2 different aircraft. SP as the unknown spoofer location, D of I and J as the respective aircraft distance, and C over V track, which relates the position change rate to the signal propagation speed. V track is the velocity of the spoofed GPS track, and C the speed of light. So notice V track cannot equal 0, there has to be movement. Spoofer localization, error minimization. As opposed to models and equations, real-world signals are subject to noise. Interpolation for time alignment introduces noise. The constructed hyperboloids don't intersect at a single point, so they only mark an area, so that's more noise. An error function is used to shrink that suspected spoofer location. It scales linearly, and more relations reduce system error. And so this equation here, the inner 2 sums aggregate the errors of relations between all spoofed aircraft. whereas the outer sum aggregates the errors over all sampled times. The argument with the minimum error is calculated to be the best approximation of the spoofer position. To further improve processing, since all aircraft considered receive the same spoof signal, the underlying track can be predicted regardless of time information. This allows subsequent filtering of spoofed aircraft positions. And cannot correct timing inaccuracies, but can better estimate the spoofer location at a single measuring time. Evaluation. CrowdGPSSec was applied to real-world open sky network data of Central Europe. This data was modified to simulate spoof data, since setting up a real-world spoofer on air traffic is prohibited, of course. Evaluation test assumes an omnidirectional antenna located directly beneath an aircraft at the exact transmission power necessary to promote lock-on. So this is ideal and optimal for the attacker, of course, because not only does it help to hide them a little bit more, but this is the most likely position to get a lock-on for an aircraft and to effectively spoof. Anything other than this setup will only aid the spoofing detection because you're talking higher transmission powers and greater transmission range, so more likelihood of being discovered. Evaluation results. For test 1, cross-checks with MLAT outperforms test 2 multiple aircraft comparisons with a 61.2% coverage versus 2.9% coverage. Both tests combined lend 8.9% coverage. Coverage is the percentage of aircraft positions protected, which are protected as effectively monitored by a test. Central Europe, of course, being as dense as it is, lends itself to test 1's strengths. With both tests combined, 75% detection at this optimal spoofer setup. Researchers say if the spoofer is not directly beneath the aircraft and uses a higher transmission power, detection rate increases quickly to 100%, although they do not state how quickly that happens or to what it exactly increases to. Test conclusions. The 2 tests can reach a detection rate of up to 75% when the attacker is directly beneath the target. Test 1 performs much better in terms of coverage and detection rate, while Test 2 performs better in terms of detection delay. The result is not surprising since the receiver density of the open sky network is high, which benefits Test 1, while the aircraft density, which Test 2 relies on, is limited due to separation minima. So think that Central Europe is dense in aircraft, yes, but we're talking high-tech aircraft, modern aircraft that are strictly adhering to separation rules, IFR separation rules. So we'll talk about this later, but also in our RVSM airspace, they have very tight altimeters. They're maintaining more, or at least 1,000 feet separation outside of RVSM, at least 2,000 feet separation. Test 1 directly depends on multilateration coverage and should therefore work better at high altitudes where aircraft are tracked by more sensors. In contrast, Test 2 benefits from dense airspaces since those aircraft protect one another. So you're thinking in approach around a terminal area, so flying into an international airport in the middle of the day, those aircraft are going to protect one another more because it'd be very difficult to pick out a single aircraft. Detection delay. Delay between when a GPS receiver locks onto a spoof signal until detection by CrowdGPSSec is what we're defining this as. For Test 1, this is a delay between receiving the ADS-B position and the MLAT evaluation update. And for Test 2, this is the inter-arrival time between spoofed position reports. The delay of Test 1 is a result of the delay of the relatively long MLAT calculations. For Test 2, on the other hand, it can detect an attack as soon as false position report is received from 2 different aircraft, so pretty quickly, which is what you see in the graph there in Figure 11. Spoofer localization performance. To quantify results, 2 metrics defined and tested in MATLAB. Distance between actual spoofer position and the experimental estimation. Constructed circle around estimated position with radius equal to the spoofer location. And this is the search area to find the attacker. To do all this, the researchers set up an area. The spoofer is randomly positioned in an exemplary area of 400 square kilometers, and its range is set to 100 kilometers, spoofing a track of 1,000 kilometers an hour. On the other hand, they are able to simulate different airspace constellations, attacker configurations, and noise impacts of MLAT and GPS. So impact of noise on GPS accuracy. The researchers conclude that noise in the reported GPS positions is a dominating factor in localization. between a few kilometers and tens of meters is what we're looking at. To find this, they imitated position reports from already spoofed aircraft by incorporating the attacker control position and adding Gaussian noise. Figure 12 depicts the impact of high GPS noise to low GPS noise with respect to spoofer distance with standard deviation error bars. The researchers also concluded that the localization accuracy increases rapidly within the first few minutes, whereas after 5 minutes the accuracy improves slowly. 5 to 15 roughly halves that distance. The impact of noise on MLAT accuracy. Researchers conclude that MLAT noise has little impact on localization accuracy. The researchers chose to vary the noise as shown in the figure, but as you can see, this had little effect. Additionally, the localization approach doesn't rely heavily on MLAT measurements of actual aircraft positions, which further insulates the localization from noise in this module. Impact of spoof track velocity. Researchers conclude there is a strong dependence on track velocity. This is due to the scaling factor. Remember when we couldn't divide by 0 earlier? This relates to the observed distance to the spoof track velocity. Thus, low track velocity results in low distance differences between spoofed aircraft, so noise becomes a more powerful detriment. As seen in figure 14, at 300 kilometers an hour from 1,000 kilometers an hour, accuracy decreases by roughly a fourth. This gets increasingly worse for lower speeds. Some discussion. Spoofer localization accuracy depends on GPS error, MLAT error, and spoofed track velocity. While MLAT noise isn't significant, a GPS noise and spoof track velocity are. If a target is stationary, spoofers can spoof constant positions. The detection will still work, but localization will fail without additional trend data, such as adding a timestamp from some sort of universal time, such as the GPS satellites themselves. This system could be applied to any other transportation network, provided there is a broadcast reception network to monitor. In conclusion, CrowdGPSSec is lightweight and utilizes an existing broadcast infrastructure. Attack detection is achievable below 2 seconds, and localization accuracy around 150 meters after 15 minutes of monitoring. Some of my thoughts from my experiences that I explained earlier. This test doesn't correct for blended INS solutions, so inertial navigation system solutions, keeping aircraft on the right path despite spoofing. It doesn't correct for pilot awareness and cross-check, which can also keep aircraft on the right path despite spoofing. Both of these could present error into the model if aircraft start advertising incorrect positions but fly the correct route, or reduces the number of aircraft being effectively spoofed, leading to an incorrect assessment on spoof location, strength, etc. Central Europe is BRNAV, which is RNP5, Required Navigation Performance 5 nautical miles. Systems certified to be 5 nautical miles 95% of the time. In reality, aircraft can be shoot approaches down to 0.1 nautical miles accuracy on blended solutions with ground-based navigation aid augmentation. And RMP is based on total system error, and that includes navigation system error, flight crew error, RNAV computation error, and display errors. So there's a lot of redundancy built into this. Central Europe is RVSM between 290 and 410, 1,000 feet flight levels, which requires 2 independent altitude measuring systems cross-checked within 200 feet and autopilots less than 75-foot altitude holding error. And RVSM allows for that 1,000 foot of aircraft separation. Outside of that is 2,000 feet, and naturally the majority of aircraft far exceed these tolerances. Naturally, regions with high air traffic below sensor density cannot be protected. So think the North Atlantic tracks, the Pacific Organized Track System, Africa, the Middle East, Asia. So this isn't quite global, but more somewhat international. Additionally, I've flown in places where even GPS signal reception is questionable, and outside the coverage of radar, military, or otherwise, so these places do still exist. We have our summary slide here. Next is the related work slide, and I'll leave that up for easy perusal. I'm not going to read these for you here. And this is the related works. So thank you for listening to my presentation. I'll leave this up, and let me know if you have any questions.